Hello everyone, welcome to our Capstone Symposium presentation. We're Team FarSounder and our project is Network Control Signaling, Precise Timing Control via Ethernet. Our technical directors are Matthew Coolidge and Matthew Zimmerman. My name is Scott Brennan and I'm an electrical engineer.
And my name is Justin Hall and I'm a computer engineering major.
FarSounder is a company that's dedicated to continual innovation in the field of marine navigation technology. FarSounder strives to be on the cutting edge of sonar technology for both private and commercial ships. FarSounder specializes in the development and manufacturing of 3D forward-looking sonar systems for marine vessels that show what lies ahead in real time. FarSounder's sonar system contains three main components: the transducer module, which is located in the water and houses the data collection system, and the power module, which is located on board and houses the transmit system electronics. Both of these modules are connected by a custom bundled cable. The cable bundle has several important functions. It transmits a sonar pulse, triggers the data collection to start and stop, transmits the data from received sonar pulses, and also sends power to the transducer module from onboard the ship. FarSounder's current custom bundled cable in use is expensive, heavy, and has a large bend radius. This makes it difficult to transport, difficult to install, and makes doing maintenance on existing FarSounder systems a hassle. FarSounder's custom bundled cable contains a transmit signal, shown in yellow, power supply conductors, shown in green, 4 digital in-out conductors, shown in red, and an Ethernet cable, shown in blue. The 4 digital in and out conductors serve the purpose of sending a trigger signal and a return signal to synchronize the data collection system with the transmit system electronics. FarSounder believes these 4 digital in and out conductors are potentially unnecessary. Since the custom bundled cable already contains an Ethernet cable, we believe we can use an existing IEEE LAN network timing protocol called IEEE PTP1588 to synchronize the data collection system with the transmit system hardware. This would allow for us to use the Ethernet cable to serve the function of the 4 DIO conductors, removing them entirely. PTP1588 works by setting up one device as a master clock and one device as a slave clock. The master constantly reminds the slave clock of the current time with very little delay, keeping the devices in sync. Our anticipated best outcome is the implementation of an entirely Ethernet-based timing solution and the removal of the 4 unnecessary digital in and out conductors.
The technical achievements that we have made this far as a team can be summarized within the following few points. Our first major task was to identify some way of synchronizing 2 clocks over an Ethernet connection. Luckily, there are a number of network protocols in existence that accomplish this, and we decided on the Precise Timing Protocol, also known as IEEE 1588. We decided on this protocol for its hardware timestamping and accuracy capabilities. The second major task was to identify a suitable evaluation board that would allow us to implement this protocol in a network environment. After much consideration, we chose NXP's MI-MXRT 1060 evaluation kit shown on the slide. This board offers one 100 megabits per second Ethernet port with support for PTP, the I.MXRT 1062 ARM-based microcontroller, JTAG and Arduino interfaces, 2 USB 2.0 ports, as well as support for many other features. Upon receiving and experimenting with our evaluation kit, our next major task was to set up a functional network interface and demonstrate a functional implementation of the precise timing protocol running over an Ethernet connection between 2 of the boards. With the goal of our anticipated best outcomes in mind, we can see that reaching this goal would have a multifaceted impact for FarSounder and their line of sonar products. For one, by reducing the number of necessary conductors in the cable bundle with the help of our Ethernet-based timing solution, we would be reducing the size and weight of the cable bundle itself. In doing so, we open up possibilities for using more off-the-shelf components as a part of the cable design, a lower cost of manufacturing the cable, and greater ease when installing the cable in marine vessels. All of these implications lead toward an estimated cost savings of $300 to $400 in regards to the production of each sonar system. Here we can see the basic operation of FarSounder's current timing solution for ensuring the synchronicity of the data collection system's records with the signals produced by the transducer module. Below that, we can see the ideal operation of our Ethernet-based timing solution. Currently, the host application that the end user utilizes to control the sonar device tells the data collection system to start collecting data from the transducer module. Upon this action, the data collection system asserts a signal on one of the conductors in the cable bundle that tells the transmit hardware in the power module to begin its task of transmitting sonar pulses. Each of these actions produces a timestamp, which is then processed in tandem with the sonar data to produce a distance measurement out of a sonar pulse. Were we to remove conductors from the cable, including those used to drive the synchronicity of these two systems, we would then need some other way to ensure that they are synchronized. Our concept timing solution accomplishes this by giving each system its own reference clock, which will be used to provide the sonar data timestamps for 0 time and will be synchronized via the existing Ethernet connection in the cable bundle.
My contributions thus far include researching several microcontroller contenders and comparing them in a spreadsheet. This is how we came to the conclusion that the NXP I.MXRT 1062 microcontroller was the best tool for the job. I also successfully tested PTP implementation and local network communication between a PC and a microcontroller. We hope that this will serve as a first step to getting both the boards to communicate with one another on their own. I also experimented with using one board as a master and one board as a slave. In the future, I plan to learn more about the file structure for projects in MCU Expresso and IAR Embedded Workshop. This is in order to migrate the AN12149 demo project, which is currently only available in IAR Embedded Workshop, to MCU Expresso, our IDE of choice. I also hope to set up one NXP board as a PTP master and one as a slave. I also plan to demonstrate the PTP sync by asserting a GPIO on both devices at the same time. Once implemented, I also plan to develop a method to test the efficiency of PTP between the two boards.
During the process of selecting a microprocessor to be used in our proof of concept, I tried to consider boards that had suitable capabilities for other hardware systems used in FarSounder's products. Some of the capabilities that we looked for include the ability to interface with a DAC, serial peripheral interfaces and I2C interfaces for communication with sensors and external memories, and multiple Ethernet ports. Features such as these are what helped us land on our decision of the MI-MXRT 1060 evaluation kit. Once we had these boards in our hands, Scott and I got to work on learning how to utilize some of the many features of our boards. One of the things that I achieved was setting up a functional network interface on the board with the help of a port of the open source lightweight IP library. Using this library and its functions, I was able to send ICMP pings to and from the device, demonstrating a fully functional IP protocol stack. Now that we are at the point where we have achieved networking capabilities with our evaluation boards, the next step is to implement the precise timing protocol in a master-slave format. I, along with Scott, am working on this by following some guides that NXP provides on implementing this protocol on their families of microcontrollers. Once this appears to be working, it is then necessary to test the accuracy of the clock synchronization method. This will be done by probing GPIO pins for a pulse produced by each of the device's clock with an oscilloscope. Beyond this confirmation, it would be ideal to test the timing implementation under other network conditions, such as with other nodes in the network besides the two microcontrollers themselves. This would be useful information, as the network conditions in which the system may be deployed could potentially consist of other hardware, such as switches and other host devices, which could affect the reliability of the timing protocol. If we can show that this solution indeed meets our anticipated best outcomes, we can then think about implementing more features of the sonar system into our capable microcontroller. Currently, we have a working demo of PTP running on one of our boards with the use of software provided by NXP. which runs as is in a paid IDE known as IAR Embedded Workbench. Ideally, we would like to port this source code to our free IDE of choice, MCU Expresso. Once this is done, we should have a baseline application for the boards that successfully synchronizes a slave clock to a master. This will allow us to then implement the control signals necessary for the data collection system and transmit hardware. We can also try to identify and realize any other cost-saving techniques that may involve condensing other functions of the sonar system into our microcontroller package, such as interfacing with the sonar stack. Again, we would like to thank Matthew Coolidge and Matthew Zimmerman for all their guidance and information that they have provided for us as technical directors. They never fail to help with any questions or difficulties we might have, and have been very supportive of our ideas and accomplishments. We would also like to express our thanks to Dr. Sunak for providing the excellent opportunity to get some great hands-on engineering experience.